All right. So far my recording has gone okay. It took me a while to come to which recording gizmo I like. I like the Screencast-O-Matic. Sounds like a refrigerator or something, but Screencast-O-Matic is what I capture your lectures in. Okay. So remember all the stuff we talked about rounding on, this is Wednesday, on Monday. We talked about rounding and such. Those rules apply whenever we do calculations, okay? And we're going to do some calculations, so we're going to use those rules. So one of the properties, actually it's a physical and intensive property. It's a physical property, it's density. And I think I might have mentioned that. When I think of density, I think of how compact something is or how fluffy something is, density. Density is just basically a ratio or division problem. What we're going to end up doing is isolating an object. We're going to grab the mass, we're going to grab the volume, we're going to do a division, and that's the density. We are going to use the symbol rho, the Greek letter rho, for density, not the capital D, okay? If we go back to the kinetic molecular theory of matter, kinetic means motion, okay? That was the one that kind of looks like this, where you have boxes representing solid, liquid, and gas. Okay, so with regard to gases, how much intermolecular bonding do we have? Lots or none? None, no intermolecular bonding. So these guys are doing this. How about solid with regard to intermolecular bonding? Lots. So it'll be kind of hard to do that, but that's, how about liquid? Moderate amount, yeah. So I'm going to kind of make this bigger. So if I could show that matter, I'd show these are my intermolecular bonds. And then here, these are my intermolecular bonds. You guys told me a moderate amount, like that. Over here, no intermolecular bonds. Cool. Well, how much motion do we have? Like over here with the gases, have lots or none? Lots of motion. So in physics, what we do is we use the length of the we use the length of the arrow to represent like magnitude. Now, not only do I have them, but I have like the. I do like this room though. Let me know if you can't hear me. How much motion do we have over here? Less. Yes, very less. All matter has motion. Yeah. And here's one of the. An interesting thing. I'm going to pick on the solid. I don't know if you buy this or not, but as we cool it down, what happens to its motion? It gets less and less. As we cool it down, it gets less and less, and it squeezes together. Exactly. So these guys down here get colder. I'm going to say, actually, as they squeeze together, your volume is going to decrease. What about these guys over here? What happens if we cool them down? They slow down and the volume's going to decrease. Exactly. So colder, okay, volume, you got it. So this is all to say that if density is a ratio of mass to volume, density's counting on you going ahead and finding the mass, which just involves a scale, and somehow getting the volume. And volume varies with temperature, okay? So if this varies with temperature, then this must vary with temperature. Does that make sense? Volume varies with temperature, so density varies. And as it turns out, your gases are your wild children, and they really are susceptible to shrinking down at lower temperatures. Your solids to a lesser extent. So here we've got, this is just trying to show you kind of just some simple dynamics of density. So solid water floats. Solid water floats. If something floats, it's less dense than the thing that's the medium that's hanging out in it. So solid water is less dense than liquid water. Talk about that here in a minute. But aside from that, can you see why is the blue, if I start out with blue dye here, and this is water, why is this blue dye going down like that? Yeah, it's more dense, exactly. It's simply trying to show you in the vicinity of that ice cube, that water, that cold water is more dense than the warmer water around it. It's just lovely. So volume is dependent on temperature. Here are a couple of pieces of glassware we use to measure volume. This is that pipette, but now the pipette that I showed you in lab check-in had only one mark, one gradation. This pipette has many gradations. To get your liquid in here, do we just suck it? We use a pipette bowl, okay? And you guys actually will be using pipettes and pipette bowls. Come on. So, anybody remember what this is? There's letter V. Volumetric flask. It's a volumetric flask. It has one mark up there. The whole volume thing, though, to show you is on, if we were to blow this up, we have TC means to contain, and it's giving you a temperature, 20 degrees Celsius. TD means to deliver, and again, we have 20 degrees Celsius. So we talked about physical and chemical properties in here. So when I take, if density is a ratio of mass to volume, when I take the mass of something, am I changing it? If I take the volume of something, am I changing it? Now, so actually I can measure those quantities, those are physical properties, and when I take a ratio, it's a physical property. Intensive, what does intensive mean? Intensive, I go with does not depend on amount, exactly. Intensive is independent of amount. Yep, does not depend on amount. I bet you buy that. I mean, the density of water 20 degrees Celsius better be constant whether I'm doing a cup or a bathtub bowl. Okay? What's kind of interesting to me is that density is a ratio of mass to volume. And I don't mean to, you don't have to get confused about anything, but mass and volume are dependent upon amount. So we take the ratio of two extensive properties and we get an intensive property, which is kind of fun. Sounds like I'm math. So density is a ratio of mass to volume. Now, units are very important. Units can save your light, your chili, or whatever. Okay? Units are important to know that you have the problem set up correctly. So we better make sure we do units with regard to density. So we're going to have units of mass and units of volume. So I would call this grams per milliliter. Like anytime you see a slash, that's per. And think of that slash as really being a divisor. So we have grams in the numerator, milliliters in the denominator, just like this. Sometimes I call it unpacking. So grams per milliliter mean grams per milliliter. It's the same thing. We can also, does anybody remember the relationship between, what if I did this? 1 milliliter is equal to blank centimeters cubed. What number goes in there? 1, exactly. And it is an exact relationship. Bless you. So those are two great volumes. So here actually, the way this works out, and I'm going to show you how to use this, what we call factor label method of getting density from grams per milliliter to density of grams per cubic centimeter. But the fact that a milliliter and a cubic centimeter are the same, does this make sense that your densities are actually going to have the same numeric value? So now down here, this is kind of interesting. If you see something raised to a negative power, that means that it is in the denominator raised to that power. So this milliliters raised to the -1 means it's raised to the first power in the denominator. Okay. Centimeters cubed to the -1st, centimeters cubed in the greatest first power in the denominator. All right. So we have some densities of some things. Check this out. I mean, gold. If you have 1 cubic centimeter, like, and remember I had those little Jenga-like things, 1 cubic centimeter, it would weigh 19.3 grams. I'm going to kind of ask I don't know whether to ask in the form of a question or just tell you, but Does this make sense that there is uncertainty, because we talked about that Monday. There's wiggle room or uncertainty in all of these measured quantities. Okay, these are not exact. It's just a physical property of this stuff. And there's a limitation to how precisely any of these are known. And they use the rules that we're going to use to round it. Okay. Here we have various liquids. What's the difference between units when we got to gases? What was different about that? It's grams per liter, yeah. So we upped it from milliliters or cubic centimeters to liters. Yep. All right, so let's do some problems coming up with density. And this is where I like to say, don't make it harder than it is. Just make it hard enough. Okay. So all we got to do is isolate an object, get its mass. It's going to go in the numerator. Get its volume. It's going to the denominator. Okay, and we're going to divide it out, and we're going to report it as density. I like these three kind of steps. The one thing I do have an issue with a little bit is I don't think, case in point, the density of gases. I don't think that your goal should, for every density ratio of something's mass to its volume, it should always be either grams per milliliter or grams per cubic centimeter. Yes? So let's do this example. And actually, this is great because you guys are going to be doing this tomorrow in lab. So we're dealing with something that happens to have nice 3 straight sides. Not everything will. But if it has, if you have a length, a width, and a height for some sort of a block, then you know how do you get area. Or not area, volume, sorry. How do you get volume? Length times width times height. That's exactly what we're going to do here in a minute. I'll warn you ahead of time. Tomorrow you guys are going to be using little blocks. And I don't care which one's your width, your length, and your height. You go ahead and get the 3 unique dimensions and write them down. Okay. So here we have the dimensions. So we can use this to get the volume, multiply each other, get the volume, and here we have the mass. So, right? Now here's where I like to tell you, in case you haven't already had a class, a science class like this that made you, you have to show all of your work. So it's not good enough just to grab your calculator, put in those 3 dimensions, the product of those 3 dimensions, and just write down on your piece of paper. You have to literally write down just like this, okay? 2.21 centimeters. And then when it's in parentheses, that's multiplied by each other, times 1.05 centimeters times 0.76 centimeters. Sometimes I'll have students that be like, Mrs. Snipes, why do you put a 0 there? Well, that's just how I learned it, and I think it emphasizes the decimal point. How many sig figs in 2.21? Figures, please. Times sig figs. I'm seeing 3. How many sig figs in 1.05? 3. How many sig figs in 0.76? 2, exactly. So we have 3, 3, 2. So if we're conservative, how do we need to round our answer? 2 sig figs. Yep. So here we go. 1.8. So we round to 2 sig figs. We're going to start from left to right, only keeping 2. Now we got the numbers part of our answer, just for the volume, and then we have the units part. Do you see where that centimeter cubed came from? Centimeter raised to the 3rd power means centimeter times itself 3 times. Centimeter, centimeter, centimeter. So that's what I mean by when you work problems, you're going to focus on the number, but you're also going to definitely focus on the units. So you need to include units as you work problem. Sometimes students, and I think this is an example of, one that you're going to see kind of a different answer up here in a minute. The question, I didn't finish the question. The question comes in, well, Mrs. Snipes, I rounded 2 sig figs, which I know I'm supposed to, but what if I use the unrounded value and carry that through to my next part? Because the next step is to take the math divided by that. Should I use 1.8 or should I use the whole number? And I think here in a minute you're going to see that in my calculator, when I did it, I used the whole number. But if I use just 1.8, it's not quite as good of a value, but it's okay. It's a good value. Does that make sense? The question is, do you use the 1.8 or do you use the unrounded value? And the next step, which is to take the mass divided by that number. An advantage of using 1.8 is that you know where's two sig figs. Because if you relieve that unrounded value, sometimes you get to the very answer, which in this case is density, and you don't round correctly. All right, without further ado, density, or rho, density is a ratio of mass to volume. So the mass was given in the original problem, 13.94 grams. We have a density of 1.8 centimeters cubed. How many sig figs in 13.94? Fingers, please. 4. How many sig figs in 1.8? 2. So we need to round to how many sig figs? 2, exactly. I'm going to just check this out. 13.94 divided by 1.8. And I get 7.74 repeating. This is what my calculator displays. 7.74. What would the units be? Yep, grams per centimeter cubed. Okay, 2 sig figs. So I'm going to keep this digit here and keep this digit here. So I would write it, what, 7.7 grams per centimeter cubed. Perfectly great. Right. Now, do you see where I have on my slides 7.9? And that's just what I just said a minute ago. That's because I used an unrounded value instead of 1.8. They're both great. But if you use an unrounded value, like how do I do that? Well, we could take 13.94 divided by quantity, 2.21 times 1.05 times 0.76. There are different ways to do this. You guys, if you kind of play around with your calculator, you know that you can store things into memory, that sort of things, to use the unrounded value. There are questions about that. Because when I do that, I get 1.90437. 2 sig figs, sorry, 1.7, no, 7.90437. 2 sig figs is 7.9. You're like, Mrs. Knight, are you serious? There's 2 right answers? And I'd be like, yes. Okay? Just the way it is. So, just to kind of recap, make sure we're on the same page. If you put 7.9 grams per cubic centimeter, yes. If you put 7.7 grams per cubic centimeter, yes. But if you put 7.74 grams per cubic centimeter, no. So, that's where I'm coming from. Okay. So, we make sure that we included, I say no naked numbers. Make sure we include units as we work the problems. And so the dimensional consistency is what I meant about the check to make sure you did the problem correctly. Just seeing those units of grams divided by cubic centimeters, and you guys told me units be grams per cubic centimeters, you're like, hey, I know that's density. That's good. So let's pick on water a little bit. Water is unique. Water is so important to all of us, but it's definitely got some interesting properties. It violates this sort of trend in a way. Remember what I said a minute ago and you guys kind of told me that as you cool something down, it goes slower, okay? And your volume's going to decrease. As your volume decreases, what happens to your density? It increases, exactly. So volume decreases, and then actually, I'll go like this. Density, your rho, increases. As you get colder, your volume decreases, and your density, your rho, increases. increases. So first off, this slide says that, and actually I'm going to put an arrow here. What does my arrow mean? You have to memorize it. I'm going to hold you accountable for a physical property of water. And actually later on you're going to need to know that water, the freezing and boiling point temperature of water are normal atmospheric conditions. But the density of water for a wide range of temperatures is 1.00 grams per milliliter. Here we go. This is a graph, and I've hidden part of the graph. I'm going to show you how that works. But if you get your bearings, it's showing you the density of water. Notice along the x-axis down here, we're going to actually go from left to right, so we're going to get colder. Okay? So when water is in its liquid stage, okay, as we get colder, the density increases, right? That's what we said. As you get colder, the density increases. Well, there about 4 degrees, it fluffs out, okay? And the way I think of it is at about 4 degrees, from 4 degrees to 0 degrees where water freezes. This is on the Celsius scale. Water freezes 0 degrees Celsius. From 4 to 0 degrees Celsius, notice that the density is decreasing. And then check this out. When it becomes a solid, it's even polar. So this crazy jump at the transition freezing point temperature of water, this crazy jump has to do with, remember we saw a video that kind of showed you the ice crystal lattice, where they were kind of H2O molecules were kind of stuck in what we call hydrogen bonds, making this hexagonal. So if you look at a snowflake, 6 sided, okay? Okay, so it makes this cool structure. It fluffs out as it transitions from one liquid to a solid. I just think that's so cool. So since the density of ice is less than the density of liquid water, that's why ice floats on liquid water. Okay. But a lot of substances that don't crystallize like this, as you transition from a liquid to a solid, it just keeps getting more and more dense. So if that was the case with water, check this out. If when you went from transition from a liquid to a solid, if it just kept getting more and more dense, think of our icebergs floating, large bodies of ice floating on the oceans. They would fall because they'd be more dense. What would that happen? What would happen there? They would displace the water that they fell into. And then if you've ever seen the movie The Waterworld, it'd be like no land. So it's interesting. So this data kind of goes along with that graph. You can kind of see the cooling down from 100 to 10. We see the density increasing. There from 4 to 2, we see the density decreasing. And here we see it fluff out for ice. All right. So density, I just like this red pen on this dude's blue shirt. Check this out. Density is equal to mass divided by volume. The thing here is basically the volume we're assuming are very similar. So if the volume is very similar, which one's more massive? The rock's more massive. So obviously the density, if you look at it mathematically, the density of the rock is going to be greater than the density of the styrofoam. Okay, and see how that all fits together. This is showing you 3 things. We have a rock, water, and styrofoam. Which one is the most dense? The rock. Which one's the least dense? Styrofoam. In case I forget to mention it, sometimes I've had students, because you guys are going to get the density of your block, and then you're also going to get the density of a rubber stopper. And sometimes I've had students play around with dish and block, float in water. Well, if it does, then its density must be less than water. If it sinks, it must be greater than water. Monty Python skit. Okay. So the second thing, in addition to the block we're going to be finding the density of, is an irregularly shaped object. It's just a rubber stopper. I call it the Crisco method. Years ago, you couldn't buy Crisco in the sticks, you had to buy it in a tub. So if you wanted a cup of Crisco, what you would do is get out your 2-cup measuring cup, you fill 1 cup with cold water, and then you would add Crisco until that water was displaced up to 2 cups. Okay? So you knew the volume of the Crisco you added by the displaced water. That's exactly what you guys are going to do tomorrow, and that's exactly what's being described here. So we know the mass of this rebar, and it says without the rebar, our grad cylinder had a volume of water in a grad cylinder was 13.5. You plunk in the rebar, make sure there's no bubbles, and it displaces now, it's up to 22.4. So how can you get the volume of the rebar? Just subtract. Yep, that's exactly what we're going to do. So we're going to subtract these to get the volume, and we give it the mass, so then now remember, one of the things you're going to be doing tomorrow is you're going to make sure that you try to estimate between gradations. You can see that here somebody has estimated, so we have 10, 11, 12, 13, 14, 15. So this is 13 point, they went ahead and said it was halfway between, so 13.5. So you're going to have to be able to do that. Added the rebar, and here's our new volume. And they went ahead and said that's 22 point, and went ahead and said that's about 0.4. Okay. You guys told me we can get the volume of the rebar now by difference. The mass in the original problem was 69.658 grams. Now again, I said you have to show all of your work, and you do. Not only for, not only because teacher said you need to get all the points possible, you have to show all of your work. But it helps you tell you what you're doing. And it helps you tell me what you're doing. Okay? You don't have to do it like this, like volume is equal to combined volume minus volume of water. But you do have to do something like this. So V, or the volume of the rebar, and no naked numbers, is equal to that displaced volume, which is 22.4 milliliters. And from that, you subtract the without the rebar, 13.5 milliliters. Now, again, we do more multiplication and division than we do subtraction and addition in chemistry. But what are the rules for subtracting? Fewest number of decimal places. How many decimal places do we have here for the word time? One. How many decimal places for that one? So we're allowed 1 decimal place. So since we're allowed 1 decimal place, it's 8.9 milliliters. All right, we're almost done, aren't we? Ratio then? And there's no, to me, unrounded value, I think. Okay, there's no trickiness to that now. All we gotta do is go back up and grab the mass, 69.658 grams, divide it by, now we know the volume, 8.9 milliliters. How many sig figs in the mass? In the 69.658 grams. 5, yep. How many sig figs in 8.9 mils? 2. So we have to round it 2 sig figs. Isn't that like wasn't that the density of our metal alloy too? Isn't that weird? Oh my gosh. 9.6. Interesting. All right then. Any questions about that? Okay, one more topic involved into this one that we need to talk about is this percent. By definition, percent means part per 100. So if we're dealing with mixture, okay, mixture, remember, is something, 2 or more things are just physically tossed together. A cool thing about a mixture is you can separate them back out into different components. So if we're dealing with kind of weight percent, if you have the mass percent of something, that number is the number of grams of that component you would have in 100 grams of the whole mixture. It's kind of unpacking that. So here's a bleach container. Here you can see 7.4% sodium hypochlorite. So if we were to unpack what that means, 7.4%, and unpack you're going to hear me use throughout the course. Sometimes just in order to use a constant, you need to unpack it. It would look like this. 7.4 grams of sodium hypochlorite per 100 grams of the solution. Now, as I unpack or go from here to here, okay, first off, how many sig figs in 7.4? 2. As I unpack, I count these as, just like you told me, 2 sig figs, and this 100 grams, that's exact. Because it's by definition, because it's percent, parts per 100. Okay, so that doesn't bring any uncertainty. All right, cool. Well, usually you don't have 100 grams of mixture. Usually you have 12 grams or 13.56 grams or something like that, 150 grams. So if you want to calculate this, the difference between unpacking and this is how you calculate it. Well, it says calculate. Okay, what you do is you take some of your mixture and you get a mass, and then somehow you isolate the component A or B or C, the component of interest, and you get the mass that's in the mixture. Okay. And then you divide, and to get it per parts per 100, you have to multiply by 100. Sometimes I'll say multiply by 100 or multiply by 100% to get mass percent. So mass percent and mass fraction are related. Mass percents are parts per 100. Mass fractions are parts per 1. So in the case of mass, it's the mass of that component in just 1 kilogram of mixture. The thing that's missing to calculate mass fraction is times 100. Right? That's it. Otherwise, it's the same thing. Oh. Forget. I don't know how long crickets live, but. So if you have mass fraction, we're going to do a problem here in a minute, and you want mass percent, all you got to do is multiply by 100. We're dealing with the same component. It's in the same amount. To get to mass fraction, it's the mass component divided by total mass of the mixture. To get the mass percent, it's the mass component divided by total mixture times 100. So let's do an example, shall we? And even a simple example like this, I like to doodle. I like to doodle basically all of my problems. I think one of the reasons I like to doodle is it stalls. It gives my mind a chance to think. Some students I've had are just the most awesome drawers. I'm like, that is so awesome. You should go into art. But this one would look something like this. I draw beakers that only I know can almost tell are beakers. They get really ugly sometimes. But this one says we are putting 5.42 grams of sucrose. And we're going to put it in a beaker. Well, I picked the beaker, it doesn't say that, but some container, and it says we've already got 28.72 grams of water, H2O in there. It says it all dissolves, that's why we get a homogeneous mixture. And we're supposed to come up with some, I'll put question mark, mass fraction, and question mark, mass percent. And then I might over here, what I just learned, what we just covered, mass fraction is going to be the mass of the component of interest. So I'll put number of grams of sucrose, because that's the component of interest, divided by number of grams of the total solution. You know, do you need to doodle this problem? Do doodling chemistry problems help a lot? Yes. Okay, so just kind of looking at this then, we can see that this 5.42 grams is going to go here. How do I get the grams of the solution? Yep, I add both of these together. Yep, and that's going to go there. Once I have mass fraction, how can I get mass percent? It's mass fraction times 1. That's the relationship between mass fraction and mass percent. Mass fraction is part per 1. Mass percent is part per 100. Just scaling it up. All right, here we go. Mass of the solution, you guys said I need to add. Now, you need to show your work, right? You need to show your work. So here we go. I'm going to write down 5.42 grams plus 28.72 grams. Put another way, if I don't see this quantity, like on your chemistry write-ups, in your calculation, I'd be like, how did they do that? So do we round according to, how many people think we round according to decimals? Me too. And how many decimals we can round to? 2. Yep, you got it. So the number that's going to go in the denominator here is 34.14 grams. Cool, we're ready to knock it out. Mass fraction, the mass of the component divided by the total mass. The mass of the component is 5.42 grams. Mass of the total solution is 34.14 grams. Okay, so how many people think we round according to decimals? How many people think we round according to sig figs? Yay! How many sig figs? I'm looking 3. I'm liking 3. Very good. Now this is one of these what we call unitless sort of numbers. So we're going to allow, I know they're grams of different things, but we are going to allow these grams to cancel. You guys told me 3 sig figs, so I'm liking 0.159 or 0.159. And there are no units. It's units. So what is that's the mass fraction. What's the mass percent? 15.9. Yep, you got it. Oops. Okay. I gotta hit myself. So that 0.159, if we were to unpack it, it would look like this. And again, sometimes you do need to unpack it. What does mass fraction mean? It means the grams, it'll be less than 1, the grams of the component of interest in 1 gram of mixture. So in this case, 0.159 grams sucrose, 1 gram solution. And here's what you guys told me. You said if you have 0.159 mass fraction, that means 15.9%. Very good. Yay! Okay. So it's not just me. I've had to yell the whole time, haven't I? Okay. Anyway, that's all I wanted to cover today. That's perfect. So this will be due on Friday. And they get the